The purpose of these notes is to give students who are absent during one of the three lectures an opportunity to get caught up, or maybe I was going a bit too fast in the notes. In any event, it's an opportunity to make sure that you can get all the notes down on paper or all the notes typed up and turned in on time. Remember, please, class notes are done in Cornell note style. Questions or prompts on the left, answers on the right, and they need to be numbered. Because this is a video, if I'm going too fast and you still have things to write down, you may pause the video and finish up. I will warn you when I'm getting ready to move on to the next slide. All right, here we go. So obviously, pulling resources out of the ground is going to disturb habitat. It's going to create waste. It's going to create pollution. All right, some metals are things that we need to pull out of the ground. We need to purify or refine them. We use them in a variety of applications. Environmental damage really depends on how good the ore is in the ground. If it's really concentrated, they won't have to disturb as much ground. But if it has a very low concentration, they're going to need to get more out of the ground to get what they need. And of course, that's going to cause a lot more damage to the environment. All right, I'm getting ready to bump ahead in 5, 4, 3, 2, and 1. All right, types of mining. So surface is what we obviously see most often. Open pits are also a type of surface mining. Huge environmental degradation. Mountaintop removal is probably the worst. That's where you literally blow up a mountain to get closer to a layer of coal. And then subsurface obviously has its own dangers. So overburden is what we call the stuff on top of the resource that must be removed before you can get to it. Contour strip mining is mostly coal and other resources that are in hilly or mountainous terrain. Mountaintop removals when you use explosives to blow up, like I said, the mountains. Getting ready to jump ahead in 5, 4, 3, 2, and 1. Oh, by this way, this word says contour, Contour. Sorry about that. So mountaintop removal, as you can see, this used to be a big mountain, and they have literally blown off this portion to get closer to the coal layer. So subsurface obviously has its own dangers, and they do subsurface mining when the deposits are deep in the Earth's crust. Other problems with the environment is sinking land. Obviously, that's going to be more common in subsurface mining. Health problems, particularly respiratory problems from breathing in bad air. And then a lot of the mining processes leach nasty stuff out of the soil and the rock, and those can get into waterways, and that's called acid mine drainage. All right, moving ahead in 5, 4, 3, 2, and 1. All right, please use this as an opportunity to look back at your notes and practice with them a little bit. 3 environmental problems associated with mining for mineral resources. Take a look back at number 1. Yeah, so stuff like disturbs the land, erodes the soil, creates solid waste, pollutes the water, air, and soil. Most damaging type of mining. Take a look at number 6. Yes, mountaintop removal. 2 environmental problems associated with subsurface mining. You might want to take a look at number 8 for that one. Yeah, so sinking land, subsidence, health problems for the employees, the miners, and acid mine drainage. Okay, moving ahead. That's some vocabulary. So tailings are rock waste that are left in piles or put into ponds where they settle out. Smelting is part of the purification process. And it uses some things that can lead to pollution. Sulfur dioxide, suspended toxic particles that damage vegetation and acidify soils, water pollution, and then tropical deforestation. It's really difficult for people in developed nations like the United States to point to these poor countries and say, don't cut down your rainforest, because in many cases, these are the only ways that the populations there can sustain their livelihood. They need to sell the trees, or they need to plant crops, or maybe they're mining the resources themselves, or maybe they're raising livestock. It's a tough situation. The developed nations need to step up and help those developing nations. Mercury is used to separate gold. In regulated mining areas, it cannot be used because it's toxic, but it's used in unregulated mining areas, especially in developing nations. I'm moving ahead in 5, 4, 3, 2, and 1. Okay, so we need to find some substitutes for the mineral resources that will run out. We need to reduce waste. It's a big one, especially in the United States. There's a lot of waste. And we need to recycle and reuse as much as possible. I love seeing the hydro flasks because you're not using plastic water bottles. And also e-waste is really important for the rare metals, like computers, televisions, electronics that are no longer working. So there's some examples of finding substitutes. The materials revolution, silicons replacing some metals, nanotechnology, graphene, and phosphorine. Moving ahead, 5, 4, 3, 2, and 1. So why recycle? So reusing resources, pardon me, means that we don't have to pull more out of the ground. Lithium is going to be really important in terms of batteries. A couple facts about lithium. It's the world's lightest metal. vital component of lithium-ion batteries, which are used in cell phones, iPads, laptops, and a growing number of other products. The problem is that some countries, including the US, do not have large supplies. Let's see. Japan, China, South Korea, and the United Arab Emirates are buying up access to global lithium reserves to ensure their ability to sell lithium or batteries to the rest of the world. The United States would probably get it on that. And within a few decades, the United States may be heavily dependent on expensive imports of lithium and lithium batteries. So just like the fossil fuel industry, the government subsidizes mining operations. They also have tax breaks for mining companies. We need to divert some of that money into better recycling programs, or recycling programs for cities or towns that don't have them, so we can start reusing more versus taking more out of the ground cheaply. Okay, moving ahead in 5, 4, 3, 2, and 1. Please use this as an opportunity to do some practice. What's the environmentally unfriendly process that purifies mineral ore? You might want to take a look back at the bullets for number 9. Yeah, that's called smelting. What is mercury used to do? You might want to take a look at number 10. So obviously it's a toxic metal, but it's used to separate gold from the ore. 2 sustainable methods for mining. Take a look at number 11 and 12. Yeah, so we got the materials revolution. We need to find substitutes. We need to reuse, especially rare metals, so recycle e-waste. Lots of opportunities to be sustainable there. Okay, moving ahead. All right, so graphene comes from graphite. Graphite is carbon. Phosphorine. P is phosphorus, by the way. Si obviously is silicon. All right, so let's get into the Earth's major geologic hazards. Pick 3 of those. So in California, we do have volcanic eruptions. Mount Lassen erupted a little over 100 years ago in 1912. Obviously, we have earthquakes because we have 2 of the 3 types of plate boundaries. Tsunamis, we do suffer from those on occasion when earthquakes happen out in the Pacific Ocean. Erosion is simply movement of sediments on the Earth's surface. And then obviously landslides are going to be common in California because we do have some hilly terrain. We do get a lot of rain because we're next to the Pacific Ocean. And sometimes earthquakes can trigger landslides. Moving ahead in 5, 4, 3, and 2, and 1. All right, so tectonic plates are these large pieces of rock that make up the entire Earth's surface. Remember, under the oceans are also these layers of rock. Under the oceans, it's referred to as oceanic crust, and on land, it's referred to as continental crust. And as you can see here in California, we have the interaction of 3 tectonic plates. We have the Pacific Ocean oceanic plate, we have the North American continental plate, and we also have this small plate that is near Mendocino, off the coast of Mendocino, called the Juan de Fuca plate. And that interaction is called the Mendocino Triple Junction, and they're going to have a significant earthquake there sometime in the next couple decades. All right, so floating rock, so the inside of the Earth is actually liquid. right underneath the thin Earth's crust, which varies anywhere from 6 to 27 miles thick, is what we call the asthenosphere. And it's basically kind of a partially liquid, partially solid layer. Think of it as like kind of goopy plastic. And then we have pure liquid, and then we have the inner core, which is solid nickel, we believe. All right, and continental drift is the idea. It's a theory that the continents are slowly moving. That's what creates earthquakes. It's also what creates subduction zones and melting of crust and volcanoes. Moving ahead in 5, 4, 3, 2, and 1. All right, so plate boundaries, we're going to abbreviate that as PB. Most of the geologic hazards we talked about earlier occur near plate boundaries. Therefore, California has plenty of geologic hazards. So we're going to abbreviate divergent plate boundary, DPB, convergent plate boundary, CPB. We have one of those in Northern California. And then transform boundary, TPB, we have one of those in Southern California, all the way up to the center of the state. San Andreas Fault kind of hangs a left and heads north west at about San Francisco and heads off into the ocean. And then, like I said, that transform boundary terminates off the coast of Mendocino. So plate boundaries, CPB, convergent plate boundaries, they move towards one another. You can see in this diagram here, one of the plates is being subducted in a subduction zone that creates a trench, a low spot in the Earth's crust. Also, when this plate melts, you'll have bubbling magma that comes up. And if it's an oceanic convergent plate boundary, you'll get volcanoes surrounded by water. That would be the Philippines, that would be Japan, that would be Indonesia down here. It also creates the Cascade mountain range in Northern California, Oregon, and Washington. A divergent plate boundary is this one, where you have plates moving away from one another. And what happens is that draws magma up to the surface, and it creates new crust on what is called a rift valley. And on each side of the rift valley, you're going to have these things that are called ridges. For example, in the middle of the Atlantic, right here, we have what is called a mid-ocean ridge. So the plates are moving away from each other in this location. And then transform. This is what's going on with the San Andreas Fault. This is a transform boundary right here I mentioned in Southern California, which goes all the way down through the Gulf of California, where plates are moving side by side. Important difference between divergent, convergent, and transform. There's no subduction. There's no new crust. You just have large pieces of rock sliding past one another at very slow rates. They liken the speed of tectonic plates moving as about the speed that your fingernails grow. Therefore, you're not going to be able to stand on a plate boundary and see them move, but you will see movement over long periods of time. All right, moving ahead in 5, 4, 3, 2, 1. All right, take a look at your notes. List 3 of the types of geologic hazards. You might need to take a look back at number number 18. Yeah, so we got volcanoes, we got earthquakes, tsunamis, erosion, and landslides. Blank plate boundaries have the plates moving away from one another, while blank plate boundaries have the plates moving side by side, and blank plate boundaries have the plates moving towards one another. You should take a look at number 23 for that one. Yeah, so the first blank is divergent, second blank is transform, and the third blank is convergent. All right, so facts about volcanoes. So active volcanoes happen where magma is coming up as a plume, or basically a big bubble towards the surface. And when it reaches the surface and finds cracks and erupts onto the surface, it can make mountains. Also, lava is certainly something to be aware of. Hot ash and gases get released into the environment, which is a form of pollution. Um, Volcanoes form the Hawaiian Islands. The Hawaiian Islands are not at a plate boundary. The Hawaiian Islands are formed over a hot spot. Essentially, you have this hole in the crust. Pardon me, not a hole in the crust. You have crust moving over this superheated magma that's come up from the center of the earth and essentially is creating new mountains. And actually, there is a new Hawaiian island that is forming on the bottom of the ocean that is southeast of the big island. And in, a couple 100,000 years, it will actually be an island itself. These are the Cascade mountain ranges. Cascade mountain ranges are formed because the Pacific Ocean is being subducted under the North American continent, and that crust gets melted and it bubbles up to form all the volcanoes in northern California, Oregon, Washington, and up into Canada. All right, moving ahead in 5, 4, 3, 2, and 1. All right, so pick 3 facts about earthquakes. This is a photograph from the 1989 Loma Prieta earthquake. If I'm not mistaken, this is a picture from the 1964 Alaskan earthquake, which was a massive earthquake. Thank goodness not that many people lived in that region when it happened. So basically, an earthquake is a breaking of crustal rock along a crack, which is called a fault, like the San Andreas Fault. Creates seismic waves, which are vibrations, and I've actually felt those waves. I felt the waves in the 89 earthquake. A little vocabulary. The focus is where the earthquake actually happens, the specific location in the Earth's crust where the movement occurs. Epicenter is usually what you hear about. That is the location on the surface of the Earth above the focus. Magnitude is the number that typically is reported. It's basically the severity, how much energy gets released. Amplitude is the size of the seismic wave, so how much motion, vertical motion, is actually seen on the ground. And if you were in the air, you would actually see these waves moving through the Earth's crust. And they're very, very difficult to predict. There is a lot of research happening, especially on the San Andreas Fault, about these things called precursors. But we're not there yet. And our primary goal with seismology is to know enough about earthquakes to help predict them and to save lives. All right, moving ahead in 5, 4, 3, 2, and 1. All right, so earthquake measurement, magnitude, we use something called the Richter scale. So minor earthquakes are going to be, 4 and less. Damaging earthquakes are going to be in the 5s. Destructive earthquakes are going to be in the 6. The Loma Prieta earthquake was 6.9. Major earthquakes are going to be in 7s. The 06 earthquake was a 7.9. And massive earthquakes, which are referred to as great earthquakes, are larger than 8. And the largest ever was Chile, was a 9.5. Remember Chile? Well, I haven't said this, but South America, same things going on. We have the Pacific Ocean plate is being shoved underneath the South American continent. Convergent plate boundaries typically have the largest earthquakes, and Chile was devastated by this earthquake in 1960. The Alaska earthquake in 1964 was a 9.4 earthquake. Remember, every step in the Richter scale, so if we're comparing a 5.0 to a 7.0, every point value increase is logarithmic, so it's a factor of 10. So a 6.0 earthquake would have 10 times as much energy as a 5.0. A 7.0 earthquake would have 100 times more energy. Sorry about that. 100 times more energy than a 5.0. And if we're talking about an 8.0 compared to a 5.0, that is 1,000 times more energy. So as you can see, as you get up into the eights, you're talking catastrophic earthquakes with lots of energy being released. Okay, moving ahead in 5, 4, 3, 2, and 1. And of course, this is the San Andreas Fault. All right, as we just talked about, every increase of 1 is equal to 10 times more magnitude. So 4 versus 6 is 100 times more energy. The seismic waves I talked about. Primary waves are compressional. They are horizontal waves. We call them P waves. As you can see, we're just talking about pressing the Earth's crust and moving in a horizontal direction. S waves, which are also called secondary waves, are the next fastest. These are typically the ones you're going to feel. Primary waves are, I've heard that they're likened to as kind of a jolt, but not kind of a woozy kind of, I'm sitting on a lake on a boat, small boat movement. Secondary have this vertical component. And then surface waves, which are also called Raleigh or love waves, they not only have this vertical motion, but they also have this side-to-side motion. So typically what happens is primary waves don't do a whole lot of damage because they're really fast. They don't spend a lot of time moving the crust at a certain location, I guess is the easiest way to say that. S waves do damage because we're talking about foundations of homes and businesses breaking. And then the slowest ones come, and these are typically the ones that knock down buildings. So damage is done with secondary waves primarily. And then the surface waves, or the Raleigh or the love waves, are the ones that actually knock down the buildings and cause buildings to harm people. All right, moving ahead in 3, 2, and 1. All right, let's practice with the notes. Describe the process of volcanism. You might want to take a look back at number 24. Yeah, so volcanoes are formed when magma, which is what we call lava under the surface, finds cracks, erupts onto the surface, and produces mountains. So actually, volcanism itself doesn't have to produce a volcano. Volcanism is just simply the eruption of lava onto the Earth's surface. What is a fault and how is it important to an earthquake? Take a look at number 25. Hopefully you wrote down what a fault is. So a fault is simply the crack along which you have movement in the Earth's crust. And faults store energy as the movement wants to occur, but it doesn't. So they store this energy, and then as soon as the strength of whatever that rock is breached, the energy gets released, the rock snaps, and that's what produces an earthquake. How much more energy will a magnitude 8 versus a 5 release? Take a look at number 27. Yeah, so basically every number is equivalent to a 0. So if we got a 3 increase, we're talking about 3 zeros. We're talking about 1,000 times more energy being released. All right, tsunami facts. So pick 3 of these. So basically there's enough movement, and this diagram really shows how it happens. So let's say we have this vertical movement along this fault. And the plate that gets shoved up in this case creates an uneven wave. And then these waves propagate towards land. And as you can see, it's really deep out here. But as this wave starts piling up, as the water gets shallower, the wave rises in size. And of course, we've had, tsunamis 10 feet, that's just simply inundate an area. We've had tsunamis with waves of 50 feet, 100 feet. It really depends on the topography, the shape of the land here, and it depends on the amount of movement that takes place. They can travel hundreds of miles per hour. So if you're out on the deep ocean, you won't even feel it go by. You won't even know. You won't really know until the water gets shallow. If you're ever on a beach and you see the beach and all the water start to rush out really, really quickly, you need to run for high ground, because that's what happens previous to a wave. Is the water literally starts rushing out, and we're not talking about a tide. That happens very, very slow. It starts rushing out, and then what happens is that rushing water comes out and it curves over and creates a wave, and then of course it crashes down when the water gets shallow here. In 2004, the Indian Ocean, there was a 100-foot wave, a 9.15 earthquake, 230,000 people died. They did not have a warning system for that one. 2011, the famous Fukushima nuclear disaster was caused by a tsunami. Basically, the water got into electrical components that are safeguards for that facility. And when those safeguards went down, the nuclear reactor got out of control, and a lot of people died. 19,000 people died. Moving ahead in 5, 4, 3, 2, 1. All right, tsunami detection. We put buoys in the open ocean and pressure recorders on the ocean floor. Some more information about nanotechnology. So we've realized that the smaller the size of materials get, they have some unexpected beneficial properties. So graphene is converted into carbon nanotubes, and it's 60 times stronger than high-grade steel. And that's important because the process of making steel releases a lot of carbon dioxide into the atmosphere. It can make cars 80% lighter, which would make them more efficient. Would require less juice in lithium-ion batteries to move lighter vehicles. That's safer. And we use it in batteries, self-cleaning glass. That's pretty cool. Waterproof coatings. But there are some toxicity concerns. Not everything's for free. Environmental benefits. So there's less mining involved, less matter and energy, less waste, pollution, removal and reduction, less need for seawater purification. Lots of benefits. Pick 2 of those. Moving ahead in 5, 4, 3, 2, and 1. What are particularly dangerous with earthquakes and tsunamis in general? You might want to take a look back at number 28, 29. Yeah, we are not very good at predicting them. And especially if you have undeveloped countries that they don't have strong buildings, and it's really, really difficult to build a new building in San Francisco. Very difficult, because the structurally they have to be so strong to withstand strong earthquakes. In developing nations, they don't have those type of regulations, and buildings fall down a lot easier, and more people die because of that. What are 2 environmental benefits of nanotechnology? Take a look at number 31, 32. Yeah, so less mining, less land disruption, less matter, less energy, less waste, less pollution. All of those are valid reasons. Major concern with nanotechnology. Primarily, it's toxicity. Some of them are toxic, which of course can lead to human health concerns. All right, ladies and gentlemen, that is it for Chapter 11. Please make sure that you get these uploaded in time in the Google Classroom, and we will see you next time.